organizers of this meeting for inviting me to this wonderful meeting. Presentations have been very informative. And I'm going to talk about the genetic architecture and prediction of complex diseases. So precision medicine is a big area, and it encompasses rare diseases, more common complex diseases, cancers, and so on. I'm going to concentrate on complex diseases. Genome-wide association studies, basically confirming the validity of the classical polygenic model for complex diseases. And finally, about polygenic prediction in complex diseases, which is then getting more translational. So first of all, a little bit of introduction about precision medicine and complex diseases. So I think precision medicine is about taking account of individual differences in the prevention and treatment of diseases. And I think prediction is the key to precision medicine, because if you can anticipate problems that an individual will have in the future, what disorder they will develop, what treatment they will respond to, and what complications they might have, then we'll be better able to prevent these problems. And of course, inherited genetic variation is one important source of individual differences. It's not the only source of individual differences, but it's one important source. And the genetic information may be used for prediction of disease risk or the stratification of patients into different subgroups, perhaps with different pathogenetic mechanism, perhaps with different response to treatments and prognosis and so on. And single gene diseases tend to be very distinctive. And patients with single gene disorder are clear outliers from the general population, whereas for complex disorders, these disorders mostly reflect pathology, which is continuous in nature. And an example of that is ischemic heart disease, which you might think of as an all or none phenomenon, but if you look at the underlying pathology, then there is a gradation of narrowing of the coronary artery, which can range from very mild degree, very mild narrowing to severe. And so it is this underlying continuous pathology which may be determined by multiple genetic and environmental factors. And of course, the prediction in complex diseases includes, but is not limited to disease occurrence, in other words, disease risk, but accurate prediction of complications, treatment response, adverse reaction, and prognosis will all benefit patient management. And in complex diseases, prediction will need to consider the involvement of multiple genetic, environmental, and lifestyle factors, as I think some of the previous speakers have already described. And so in order to consider all these factors, we really need a very solid framework to integrate these factors. And I'm a little bit dubious that throwing everything into a neural network will work. There's probably too many variables and not enough subjects. So this is a small summary of the introduction, that prediction is central to precision medicine, and that second point, the prediction in complex diseases requires a solid framework for integrating genetic, environmental, and lifestyle factors. So the second part of my talk is to introduce the classical genetic models, which were developed for continuous variations such as height, weight, and other measures that are quantitatively variable. So it was originally developed by Ronald Fisher, who showed that the family data on continuous variation was consistent with polygenic model, whereas previously biologists have debated whether continuous variation had some other kind of determination rather than gene. So I think Fisher's work showed that continuous variation was consistent with polygenic model, that there are multiple genes involved. And of course, when you have multiple vectors, you naturally lead to continuous variation. So how does that explain diseases that appear to be all or nothing? And the liability-threshold model was proposed by Faulkner to resolve that issue. So the proposal is that there is an underlying liability, which we do not measure, and when that liability exceeds a particular threshold value, disease develops. So the model, the polygenic liability threshold model, can be explained often by genetic counselor using this kind of analogy that you have two different types of marbles, with one color representing genetic factors and another color shape representing environmental factors, and that an individual is like a jar, and the jar can be full to a various extent with these two types of marble, and then when that jar is full, then disease develops. So the extent of the jar is full is a liability, and the level at which the disorder develops is a threshold. And I think Dr. Bendler actually used something similar, but went further and having marbles of different sizes. So you have the rare, huge marble that one will fill up the jar equivalent to many small. So in classical genetics, before the days of being able to measure DNA, twin and adoption studies were used to separate genetic from shared family environmental factors in explaining familial resemblance. And the objective is often to estimate the quantity of heritability, which is the proportion of population phenotypic variation that is explained by genetic differences. So heritability can range from 0, when all the factors are environmental, to 1, when all the factors are genetic and there's no environmental factors. And you can see here a cartoon that combine twin and adoption studies, because these are twins which were reared apart from an early age and eating with each other for the first time and having very similar characters. So they will certainly strongly support a very high genetic component in these traits. So for complex diseases, there's a range of heritabilities. Most of the traits have either moderate to very high levels of heritability, so range from perhaps 20% or so of certain cancers to 70 or 80%. So I'm a psychiatrist, and schizophrenia and autism have heritabilities of 80 to 90% estimated. In addition, twin and adoption studies can also help to estimate whether two disorders share some of the genetic and environmental influences. So in other words, genetic or environmental influences that affect the risk of both these disorders. And this is achieved by looking at the cross-trait, cross-twin correlation in twin samples. So whether the trait 1 in twin 1 is correlated with trait 2 in twin 2, and whether that correlation is greater And the same is observed for other pairs of psychiatric disorders such as bipolar and schizophrenia. So in summary, for this section, polygenic liability-threshold model incorporates multiple genetic and environmental factors in complex diseases, and there's evidence of shared genetic and environmental factors on related complex diseases. And finally, the polygenic model provides a possible framework for prediction in complex diseases. But first of all, we need to really find out whether the polygenic model is actually a good model for human complex diseases. And this is where Genome-wide association studies come in. And indeed, until recently, until the last 10 years or so, it's been rather controversial how polygenic complex diseases are in humans. And this is because these classical genetic studies, like twin studies and adoption studies, they are actually not very good at estimating the number of loci involved in the complex disease. Basically, you can't distinguish whether there are just 5 or hundreds or thousands. It just doesn't have the statistical power to discriminate, to accurately estimate how many loci are involved. And so this is why that even though experts, geneticists, knew that gene mapping methods, traditional gene mapping methods based on linkage in family, would only work if very few loci are involved, were oligogenic rather than polygenic. Nevertheless, for almost 2 decades, that was a lot of people did these studies because you had to be optimistic. Because you don't know whether it's oligogenic or polygenic, so you will tend to be optimistic, get funding, and do these studies. But unfortunately, these linkage studies for almost at least a decade, probably more than a decade, in complex diseases produce very few reproducible findings. And I think many of my earlier colleagues and students actually did the linkage, including Mingwei here, and produce some interesting findings, but many of them are not reproducible. And what made a difference is the technological advances in the cataloging of single nucleotide polymorphisms and the development of technologies that allow these polymorphisms to be assayed in a very high throughput and economical manner. So in the human genome, there are approximately 10 million single nucleotide polymorphisms, common polymorphisms. And we don't need to assay all of them because they are correlated. The SNPs that are near to each other tend to be correlated, so that if you know the genotype of one, you can guess the genotype of the next one. So in order to screen the entire genome, you just need to design a set of SNPs that will together cover all the variation. And this was helped by the HAPMET project, which characterized the correlational structure between SNPs in the genome. And the University of Hong Kong took part in this project. So this made genome-wide association studies possible. Basically, you collect a sample of subjects, typically cases and controls, or it can be a population, or a sample of a population if you are studying a quantitative trait, such as height. You don't have cases of control, just looking at quantitative variation, and then you use these SNP arrays to obtain the genotyping data, and then you compare cases and controls in terms of allele frequency for a disease trait, or you just correlate the genotype and the trait value if you have a quantitative trait, and then you try to identify polymorphisms that are significantly correlated with the phenotype. And the field, I think, was facilitated by the development of software to analyze these large data sets, and it was my former student, Sean Purcell, who developed with me and other collaborators at the Broad Institute the same software, which has been widely used. And this field has been enormously active in the last decade. So Fisher wrote his recent review, a decade of genome-wide association studies charting the increase in the number of associations found over the years. And so by now, there are now over 10,000 genome-wide association, significant association with complex diseases and traits. This is one example. I give it because I'm a psychiatrist. So for schizophrenia, 3 years ago, 2014, there was this paper from the consortium which combined data from about 40 different centers. The combined sample size of, I think, almost 40,000 patients and an even larger number of controls. And using that big data set, they found genome-wide significant association from at 108 independent genetic loci. This is the Manhattan plot. And if you look at these associations, then you would see that the odds ratios are uniformly very small. So apart from a couple here, they are all less than 1.2. So effect sizes, very small. And there is one particular one that stands out, HLA, because HLA is a very complex region. And it could be that this is more than one association, but nevertheless, there was a recent study that showed some evidence that perhaps this signal is due to variation in this gene, C4A, which interestingly functions during brain development in synaptic pruning. And another finding, which psychiatrists found very satisfying, is that the gene DRD2, which goes for the protein, dopamine receptor type 2, which is the drug target of all antipsychotic drugs that are currently used. So all currently used drugs to treat psychosis work by blocking dopamine D2 receptor. And the fact that this is one of the hits gives us a lot of hope that the other GWAS associations may be useful drug targets. And I mean, another observation, implication, is that a small effect size is compatible with the gene being a drug target. This is an example. There are also other examples, and this is because the genetic variation may be only changing the gene function by a very small amount. Whereas if you design a drug to target it, you can theoretically have an effect on the function of the gene by a much bigger amount than the natural genetic variation. Another bit of insight from these genome-wide association studies is that if you were to take all the genome-wide significance lists and add up how much variation in the phenotypic variants it accounts for, they only account for a small proportion. In other words, there must be a lot more genetic variation affecting the phenotype than these genome-wide significant hits. And my former student, Hong-Chang, was one of the people who wrote one of the earlier papers showing that. But of course, because of the problem of statistical power, just because a SNP does not reach statistical significance doesn't mean that it doesn't have an effect. Because with increasing sample size, these SNPs that have marginal p-values will eventually become significant. And so there are a lot of true association below the threshold for genome-wide significance. And methods have been developed, statistical methods, to estimate the overall contribution of all SNPs to the variation of the phenotype, including the significant and the non-significant SNPs. And these are two with such methods, based on mixed linear models called GCTA, another one called LD score regression. So I'm not going to go into the methodological details of these methods, just to say that they can be used to give rise to estimates of the total contribution of SNPs, whether they are significant or not. And even if you were to do that, it's true that the total variance in liability accounted for is increased to about 25%. You can see here the total amount of the heritability explained by these SNPs. Plotted for different disorders, you can see they are in this range of perhaps 0.2 or so to nearly 0.3. But these heritabilities are still much smaller than the heritability estimated from twin adoption studies for these disorders, which are typically like 60 to 90%. So there's still a big gap. And of course, one possible source of this missing heritability are rare variants which are not captured by these SNP arrays. So in order to study these rare variants, we need to have sequencing technology, either exome sequencing or whole genome sequencing. But of course, because these technologies are more expensive per sample, the sample sizes of these studies are lagging behind the sample sizes of Genome-wide association. And I think really we don't really know the answer to this. How much of the missing heritability can be explained by rare variants? This question has to be settled by large-scale whole genome sequencing studies, which I think will be coming in the next few years. But I'm not going to go any further into that because in this talk I'm concentrating on common variation. And another insight from GWAS on complex disorders is that there is genetic correlation between many diseases. So psychiatric disorders show substantial shared genetic influences. You can see here plotted with co-heritability for different pairs of psychiatric disorders such as schizophrenia and bipolar disorder and major depression, schizophrenia and major depressive disorder, and so on, major depressive disorder, ADHD. You can see that for these pairs of disorders, there's substantial genetic overlap or shared genetic influences. And this also applies to other clusters of related disorders. Here, so the psychiatric disorders are down here. So you can see disorders to do with obesity. So these are metabolic disorders, BMI, obesity, fasting glucose, and so on. Type 2 diabetes. So they have shared genetic influences, and then cardiovascular diseases, coronary artery disease, LDL, triglycerides, and so on. And here, these are traits to do with the body size, height, head circumference, birth length, birth weight. So those are, they have a lot of genetic overlap. So shared genetic influences are very common. That suggests that many genes have pleiotropic effects, that the effects are not specific on one disease, but the effect may be on multiple diseases. So in summary, GWAS has shown that most complex diseases are highly polygenic. The classical polygenic model is pretty good description of complex diseases, pretty good model. Some heritability remains unexplained by common genetic variation captured by GWAS, which leaves room for other types of variation, particularly rare variants. GWAS have confirmed substantial shared genetic influences on related complex diseases. So twin studies already hinted at this, so it's been confirmed by genome-wide association. So the last part of my talk is on polygenic prediction in complex diseases. So, of course, with the effect size being so small, any single SNP is not going to be very useful in prediction. But, however, if we were to combine the effects of many SNPs into a single score, polygenic score, then this combined score may be able to predict risk and also may be able to classify or stratify patients into subgroups. And in calculating these polygenic scores, the SNP genotypes are weighted according to the estimated effect size, in other words, the regression coefficient from the GWAS. And usually, SNP with a p-value of greater than a particular cutoff are excluded, they're regarded as noise. Just adding noise and not adding to the information. And the first study that calculated polygenic scores was a study on schizophrenia, and first author, again, was my former student, Sean Cassell. I often think that my former students are much better known than I am. I probably should be introduced in terms of being the former supervisor. Anyway, I mean, he was the first one to calculate polygenic scores in a publication, and the polygenic score that he calculated for schizophrenia significantly discriminated patients and controls in independent samples. That's important. You mustn't evaluate how, whether there is discrimination based on the sample that you use to derive this form. It has to be on an independent sample. And indeed, they show that it did. But furthermore, the polygenic scores for schizophrenia also discriminated the patient with bipolar affective disorder and control. So again, confirming evidence for shared genetic influences between these disorders. And then reassuringly, the polygenic score for depression didn't discriminate patients with other disorders on control, like coronary artery disease, Crohn's disease, hypertension, and so on. So the shared genetic influences only apply to disorders that are sort of clustered together, psychiatric disorders, metabolic disorders, and so on. And exactly how these polygenic scores can be calculated, there are different proposed ways of doing it, but most of the methods have to involve some kind of shrinkage that usually very weak effects are thrown away altogether, and also need to remove redundant SNPs because SNPs are correlated because of linkage disequilibrium, they are close together. So, but exactly how this is done depends on the method, and there have been several proposed methods, and my postdoc, Tim Mack, proposed one of these methods called lasso sum. So lasso is a well-established statistical method for penalized regression, designed to handle situations where you have more variables than you have subjects. So, the P greater than N problem that was mentioned already. And then there is another method which is called LD-PREP. So this is a full Bayesian method, very sophisticated, needing very heavy computation. And then the simplest method is p-value thresholding. It basically just throws away all SNPs with a p-value of greater than a certain threshold after some kind of clumping to remove redundant SNPs. And I'm pleased to say that lasso sum seems to perform pretty well. LD-PREP theoretically is very attractive, fully Bayesian, but I think it is difficult to implement, and it often run very slowly and often the unstable. So anyway, not going into too much technical detail, the polygenic score of an individual is really a measure of the underlying polygenic component. I mean, that it should be a true underlying polygenic component, and the polygenic score is a measure of that, the true polygenic component of the disease liability in that individual. And the accuracy of the polygenic score depends on the accuracy of the effect size estimates. So if we know the true effects of every SNP, then the polygenic score should be perfect. But because we can only use these estimates then the polygenic score is not perfect. And the extent that the SNP effect size estimates are accurate depends on how big the GWAS is. So the bigger the GWAS, the more accurate the effect size estimates are, and the more accurate is the polygenic score as a measure of the true underlying component. But of course, to the extent that the polygenic score does not accurately measure the underlying polygenic component, it will explain less variance of the disease liability than the heritability. So the maximum amount of variance that can be explained by the polygenic score is the heritability. The polygenic score cannot explain more than the heritability. And this is a graph done by my research assistant, Ian Italian, and they're looking at how perfect the polygenic score is. So this is the R square, the correlation square, between the calculated polygenic score and the true underlying polygenic component. And of course, if the polygenic score is perfect, then the correlation would be 1. And this plots how perfect the polygenic score is as a function of the sample size of the GWAS, or a quantitative trait with a heritability of 0.5, assuming you're doing a random population sample, and that the number of SNPs is 1 million. And there are 4 plots for 4 different levels of complexity of the phenotype. So pi 0 is the proportion of SNPs that have no effect. So the simplest case is that when vast majority of SNPs have no effect, only 0.1% have an effect. So these SNPs with an effect will have quite a large effect compared to the most complex situation here, that half of the SNPs have no effect. So the other half of the SNPs have an effect, so the effect size will be very tiny. So not surprisingly, when the complex trait is very complex, even with 1 million SNPs, the polygenic score is still far from perfect. You really need even bigger than 1 million people in order to obtain a polygenic score that approaches perfection. Whereas for the simplest scenario here, that if you have a sample size of, say, 500,000, then probably your polygenic score is measuring the underlying polygenic component perfectly. And this kind of sample size, 500,000, is now already possible because the UK Biobank already has collected 500,000 subjects. And as I said, the maximum variance explainable by the polygenic score is the heritability, and you can plot the polygenic score against the disease risk for different levels of variance explained by the polygenic score. And then you can see that the smaller the variance explained by the polygenic score, the less steep is this line. So if the polygenic score explains 90% of the variance of the liability, then you have this most steep curve where the risk is almost 0, and then it starts to take off for the individual with the top 30% of the distribution of polygenic score. And that was work by Hong Chen-So, and again, this is also work by Hong Chen-So on prostate cancer, and using these assumptions, lifetime risk of 7%, heritability of 45%, and assuming perfectly measured polygenic score, and then the risk of the population of prostate cancer can now be spread out. Instead of everyone having a predicted risk of 7%, some people with extremely high polygenic score now will have predicted risk of 50-60%, whereas others at the other extreme predicted risk of almost 0%. And in addition to the polygenic scores, another source of information on the polygenic component is family history, the affection status of family members. And in order to make these exact predictions, we need to assume a model. And the classical polygenic liability threshold model provides such a model. Okay, so the model liability-threshold model that we introduced, there is a liability for each person. So for a family, every individual will have a liability, so you end up with a vector of liability, and the model assumes that this joint distribution is multivariate normal, and that we have to basically specify all the correlation between every pair of family members, and that is basically a function of the relationship, the kinship coefficient, and the heritability of the trait. And then there are certain assumptions, because this is a simplification. And when we use family history to predict risk, it's equivalent to conditioning, so that if you have two individuals, the distribution is bivariate normal, and then when you have information about the affection status of one individual, basically you are restricting that distribution to exclude the part that you know is not true. So say if one person is healthy, then you know his liability is below the threshold. So everything above the threshold is eliminated. And then if someone is affected, then everything below the threshold is eliminated. And then you end up with a conditional distribution or posterior distribution. And my former student and postdoc developed a program basically to implement this model. And this is an example family, affection status indicated by the color, and then conditioning on these affection status, you can then calculate the posterior distribution of liability, and therefore the probability of exceeding the threshold, which is the disease risk. And then the nice thing about this model is that it now has a framework where you can incorporate polygenic score. So then you can jointly incorporate family history and polygenic score. And basically, all that requires is to introduce new elements in this vector of liability. So the polygenic score can be introduced by new elements, and then all we need to specify are the correlations among polygenic scores themselves, which are only determined by relationship, by the kinship, and the correlations between the polygenic scores and the liability. And this is determined by how good the polygenic score is. A measure of the liability. And the result is that we can have a model which has a strong validity from classical genetic in order to combine these information and, for example, to predict risk of breast cancer as a function of both family history and genetic risk score. So in this plot, the genetic risk, the population is stratified according to the genetic risk, the polygenic score, from the lowest polygenic score here to the highest. And of course, the implication here, Dr. Brenner already mentioned earlier, is that for people with lower polygenic score, you can start the screening later because the risk is lower. This is a risk, 10-year risk of breast cancer, whereas people with higher polygenic score, the screening can start earlier because they reach a certain risk at an earlier age. But then once you incorporate family history, then for people who also have a family history and a high polygenic score, the age of beginning screening can be shifted even earlier. So that was work again with so. And so in summary, the underlying polygenic components of liability individuals can be measured by polygenic score that combine phenotypes of SNP according to the effect size estimate from GWAS, and to obtain polygenic scores that accurately measure the two polygenic components. Very large GWAS are necessary, that the accuracy of genetic prediction is ultimately limited by the heritability. If the disease is not very heritable, then of course the genetic prediction is not going to be very accurate. But family history information can be used to estimate the underlying genetic polygenic component as well. And of course you can, as I showed, you can combine polygenic for family history and also other risk factors under this model to make that prediction. So that's all. So overall summary, probably don't need to read it because I already summarized as I went along and I used up my time. Thank you very much for your attention.